I'm Doug, Stand-Up Physicist. Try and remember Newton's law of gravity. It's got a minus sign, a constant g, one mass times another mass, all over r squared. Now try and recall Coulomb's law of electrostatics. That's got a plus sign, some constants, one charge times another charge, all over r squared. And you look at these two, and you say, very similar. I bet they are intimately related. And yet, if you study a lot of physics, you'll eventually find out that general relativity, how we explain gravity today, doesn't fit with the rest of physics. It doesn't fit because it has resisted over 75 years of efforts to quantize it. This is the biggest problem in physics today. In the next series of shows, I am going to try and recreate a 3-day lecture series I gave at MIT's Independent Activities period. Now, at the first day, 20 people showed up. And at the second day, 8 people showed up. And at the third day, all of 4. So, well, maybe it'll be more popular now. I'd like to show you that I'm really kind of a retro guy. I'm from the class of 1984 at MIT, and my operating system on my computer is based on Unix, which is from the 1970s. My hairstyle is supposed to be a flat top from the 1950s. Every weekend I dance the Lindy Hop, which is from the 1930s. The math I use is from the 1800s or earlier. And I'm trying to solve a problem that first appeared in 1760. So I'm as retro as you can get. But I'm also modern. I know how to dress in black. I also use lots of open source software. And my distribution is Debian Linux. And I use Wimpy Point and TechMax from France and the GIMP for the slides that you're going to see. Now, all this information is available on the web via HTML or PDF, and hopefully I'll set up a webcast of this type of broadcast. So let's just get started. I have to move over to the side here. I think just about that much or so. Let's see. Okay, great. So, the title of this lecture series is Unifying Gravity and Electromagnetism by Analogies to Electromagnetism. Now, in day 1, I'm going to give you the big picture, why this should all work. And then I will go into the sorts of things that I've got to do in this lecture series, must-do physics. I will introduce tensors, what they are, and why that math tool is so necessary to doing real physics. That will actually be the end of show 1. In show 2, we'll do units, because if you don't have the units right, you're wrong. And then we will do the Lagrange density, everything that can happen inside of a box. Okay, so what is the big picture? One you could explain to Mom. Well, I'm sure Mom is familiar with these. This is the slinky. And the key property of the slinky I want you to point out, other than it's fun, is that it has this property of going here and there and back again. How is gravity like that? Well, if we think of this tennis ball here as the sun, and this thing as the earth, we've gone around the sun about 4 billion times. So here, back, here, back, here, back. Very slinky-like. How is light slinky-like? Well, I've got a few 650 watt bulbs here, and what they're doing is they're heating up electrons red hot. And so these guys are vibrating, vibrating, vibrating. They get so hot that they release a photon, and release a photon. That's what they're doing. there's an important qualitative difference between the two. With electromagnetism, light moves one direction and it kind of vibrates perpendicular to the way it moves. That is called a transverse wave. Now, with gravity, I'm going to argue that it is a longitudinal or scalar wave. This is a little bit edgy, okay, but let me explain how a thought experiment to show it. There are these things called neutrinos, and neutrinos stop for nobody. They can go through 27 light years of lead and only have a 50% chance of stopping. They just ignore everybody. So, in this thought experiment, I have this magical cup that actually can hold neutrinos inside of it. And, I dropped it. So what happened to my cup of neutrinos? Well, it did what everything else does. It started falling. And the cup, you could hear it. It found the floor here and it stopped. But the neutrinos, they would keep going. They would keep going and accelerating, actually, till they got to the dirt below this building. And then what would they do? They'd continue. They continued 100 feet down, and they'd still be accelerating. They'd go a mile down, 10 miles down, 100 miles down, still accelerating. 1,000 miles down, 10,000 miles down, accelerating and getting to such an enormous speed. Well, we could calculate it, but I'm not going to. They'd whiz past the center of the Earth. And as they went past the center of the Earth, they'd actually start to slow down. And they would slow down until they got to the antipod. A word you don't get to use every day, but it's just the opposite side of the Earth. At its antipod, it would come to a complete halt and then start falling again. And picking up speed till it goes by the center of the Earth and then slows down. And in an hour and a half's time, it would come back right back to here. And it would keep on repeating this cycle. Up and down. Probably for millions of years. But the important point, actually, is that the direction it's moving is exactly in line with the direction it accelerates in. And that's the calling card of a longitudinal wave. So the big goal here is to come up with a four-dimensional wave equation where two modes are transverse modes that do the work of EM. Nothing radical about that. But that the other two modes, a scalar mode and a longitudinal mode, do the work of gravity. That would be radical. That's what we're going to try and do. So what do we have to do? Oh, quite a bit. This is the sort of stuff we have to do to cover gravity. We first have to show that like charges attract. That you can get with a force equation with a plus sign in there. We must show why there is just one type of charge, that positive mass charge. We must recover Newton's laws of physics. And we must show that our theory generates a dynamic metric. Because all modern theories have to do that to be consistent with experimental tests. What do we have to do for electromagnetism? Well, this time, when we have the same charges, they repel. We can do that with a force equation where we've got a positive sign in there. Then we must show that there are two distinct charges. We must get all of four Maxwell equations, those that are for the source equations and those that are for the homogeneous equations. And we need to get the Lorentz force law. What must we do for quantum mechanics? We need to show why our theory can be quantized. We need to show how it's going to integrate eloquently with the standard model. And we hopefully will get some indication as to what mass is all about. That's a big hurdle to clear, but hey, physics is tough. Now, what do we need to accomplish as far as experimental tests? Well, we are doing a lot of work to try and detect gravity waves. And we want to see if this theory predicts anything about those types of results. The classical Big Bang model has some problems. One is that mathematically it's not stable. It's kind of like balancing a pencil on its point. It's going to fall over, and that doesn't seem like the right thing. It should be a stable solution. And every bit of matter that was moving back then was moving at the same speed. And yet our laws don't indicate why that should be so. So we need a solution involving gravity that is stable and has constant velocity. Then we've got a problem explaining the rotation profile of thin galaxies. The stars that are way out there, they're all traveling the same darn speed. But if you use Newton's law, it says those guys that are further out should be slowing down. This is a big problem. Another big problem that's not as well known is that if you take this nice disk galaxy and you give it a little bump or two, it should curl up into a ball. And it doesn't do that. So we need, again, a constant velocity, stable solution involving gravity. So if you find one, it might solve two very different problems. That'd be cool. So now I'm going to discuss tensors. Now, a lot of other programs on the theoretical physics on PBS and cable, they just don't do tensors because tensors are too difficult. I don't think so. They just have a bad rep. And so I'm just going to teach you some of the basic words for dealing with them. And then you'll be able to deal with them. Won't be so tough. I'll tell you what simple tensors are. And then I will discuss contravariant versus covariant tensors, how to go from one to the other, how those two actually can contract and form a scalar. I'll talk about symmetric versus antisymmetric tensors, and I will go into derivatives, both in flat and curved spacetime. So let's talk about simple tensors. Why deal with tensors in the first place? Well, tensors do a couple really good things. One is they are true no matter what coordinate system you use. Let's say you've got a coordinate system that's like a box. Yeah, these are very familiar. Yeah, length, width, depth. And that's great for describing boxes. But if you had a basketball, it'd be better to have a coordinate system that was spherical, that depended on, say, the radius of the ball and, a couple of angles. Well, if you write something in terms of tensors, then it will be true no matter what coordinate system you use. Or maybe I should say you don't have to modify the equation itself. The tensors will kind of take care of it. You don't have to worry. Another great property of tensors is that they can work in an arbitrary number of dimensions. They can work in 10 dimensions, 11 dimensions, but let's get real. We really only have one time dimension and 3 space dimensions. So in this series of talks, I will only deal with 4 dimensions. So the basic tensors are the scalar, or rank 0, and I represent that visually as a dot. It really is just one number. And then there is the 4 vector, or rank 1 tensor. And that's got 4 components. I got a donut to kind of represent the time thing, and then arrows sticking out to represent the 3 dimensions of space. And then there is a rank 2 tensor, and that is kind of like a piece of graph paper where we got 4 here, 4 there, so 16 boxes for the numbers to live in. All right. Now, what is a covariant vector, and how does it differ from a contravariant vector? Well, a covariant vector has the indices down low, and a contra has the indice up high. Now the contravariant one, all the terms are positive. And so I represent that as the donut with arrows pointing out of it. A covariant vector, it's got the same donut. Don't play with the donut. But the arrows are all pointing inwards. And those are all negative. Okay, and that's about it. But how do you go from a covariant vector to a contravariant vector? Well, you use something called a metric tensor. It's a rank 2 tensor. So let's say you have a contravariant tensor, it's up there, and you want to get it down low. Well, you hit it with a metric tensor with 2 lower indices, and that kind of drags it down. Let's say you had a metric tensor you had a second rank tensor and the indices were both low, and you wanted to raise it up. You would need 2 metric tensors to lift it up. That's how you convert. Now we'll discuss Einstein's summation convention. If you have a covariant vector and a contravariant vector, and they've got the same, index, like mu, what you can do is you can sum these two. Add together the 0 part, the 1 part, the 2 part, the 3 parts. And you end up with a dot, a scalar. Now Einstein, when he was writing a book on this, was talking to his publisher who had to arrange all these things by hand. And he said, "You've got so many summation signs in here. I don't know that I can do this book." And so Einstein came up with his convention, which was if you have a lower indice and an upper indice, it means that really you're going to sum over 0, 1, 2, 3, and I'm just not going to write it out for you. You're going to end up with a scalar, and that's the important thing. That's how you go from two vectors to a scalar. Okay, so what is a symmetric tensor and what is an antisymmetric tensor? Well, if you have a rank 2 tensor and it's got these 2 indices and you exchange them and absolutely nothing changes, then what you have is a symmetric tensor. Now, if you change these two and everything flips sign, then you have an antisymmetric tensor. Now, if you take these 2 indices and you turn them around and you get a mess, that is an asymmetric tensor. But the deep lesson to know is that every asymmetric tensor can be represented as the sum of a symmetric tensor and an antisymmetric tensor. So I show over on the side there a asymmetric tensor. There's no pattern there. And then in the middle is a symmetric tensor. Now I formed it by taking things across the diagonal, adding them up, dividing by 2. We call it average Joe. And then the tensor closest to me is the deviation from the average necessary to get back the asymmetric tensor. So average Joe and the deviance together make up the asymmetric tensor. All right, now we're going to have to take derivatives. Derivatives are how things change. And since I'm in space-time, I'm going to be concerned about time and 3 dimensions for space. So there will be a covariant 4 derivative and a contravariant 4 derivative. And just to make things a little bit more difficult, the sign conventions change. But there's a good reason. And that is if you think about derivatives, It's kind of like dividing in a limit process. And it's that dividing part that makes the conventions change. So a covariant derivative is going to have all positive signs, and a contravariant derivative is going to have the same sign for the time part, and the three spatial parts will be different. You should know about the comma convention, because you can write the derivative either as that d with the index, or you can write comma the index, and it means exactly the same thing, no difference at all. So what happens if you take a covariant derivative and a contravariant derivative? Well, by Einstein's summation convention, boom, you're going to get a scalar. And that scalar will be the second order time derivative minus the Laplace operator. But actually, the most important thing to think about is how this discussion relates to the previous slide. Because if you take the 4 derivative of a 4 potential, what you end up with is a rank 2 tensor. And it's a mess. It's an asymmetric tensor. But we can split it in two. We can look at the average amount of change in the potential tensor. That, I'm going to eventually argue, is all about gravity. That's a radical idea. Then there is the deviation from the average amount of change tensor. That is all about electromagnetism. There's nothing radical about that statement. But together, this asymmetric blobby thing will be able to do both gravity and electromagnetism. That's the technical hope. Now, what happens in curved spacetime? Well, this metric is supposed to be a measure of distances between things. And in flat spacetime, it's always the same one. But in curved spacetime, it depends on how much space is curved. So how do you deal with that when you start taking derivatives? Well, the key is that you take the normal derivative and you add in how much the metric changes. How do you figure out how much the metric changes? Well, you use something called the Christoffel symbol of the second kind. We're not going to go into the details of that. But perhaps the one important thing to notice about it is that because it's the change in the metric, and the metric is symmetric, the Christoffel is also symmetric. And we can use the semicolon convention, which indicates that I'm not only taking the normal derivative, but I'm throwing in this Christoffel with it. So if you take a derivative, that's a covariant form, it's the normal minus this change in metric term. And then you can do all kinds of crazy combinations. But the most important thing to notice is that if you have an antisymmetric tensor, where if you change the indices, everything flips around, it's actually going to throw away the Christoffel symbol automatically on autopilot. So if you have an antisymmetric tensor, it can say nothing about how the metric changes. And how a metric changes is what gravity is about. So I said the antisymmetric tensor was about EM. It is. It's about those deviants. And it has not a thing to say about gravity. That's cool. Because we're also working with a symmetric tensor. And a symmetric tensor is going to keep the Christoffel symbol. It's going to be there. It's going to say how the metric changes. And because it's there, it may give us a handle to deal with gravity as a dynamic metric theory. So, what have we accomplished in this lecture? Well, we just got through with a description of tensors, the basic math tool that we need to handle this topic. And we've gone over quite the long list of things that we must accomplish if we have any hope of unifying gravity and electromagnetism by using the tools of electromagnetism. Thank you very much. Bye-bye.
All the girls in the classroom think he's sandals with the white socks. He hears him giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
G'day. I want to make perfectly clear that no duck was harmed in any way in the preceding video. But I can make you no promises about what happens afterwards. Love burning rubber.